Hi, everyone. Welcome to the final segment of Lecture 3 of Astronomy Geoscience 160, Life in the Universe. This lecture segment will talk about what stars are made of and will help us understand how we learned what things in the sky are made of, even though we can't actually go towards them and take a sample of them. So, recall from our last lecture that if you take some hydrogen gas, you put it in a cell, you send electricity through it, and you look at the light that's produced as that hydrogen glows, and you look at how much light is produced at different colors, you will produce a pattern that looks like this, where you have different bands of color corresponding to different energy level transitions from the electron in the hydrogen atoms. This is hydrogen's spectral fingerprint. If you look at hydrogen anywhere in the universe, it will produce a pattern that looks like this, where you have light in these specific colors of light. If you wanted to plot this on a graph, what you would do is you would plot on the y-axis how much light is being emitted, and on the x-axis every different color or every different wavelength. And if you did that, you would get a graph that looks something like this, where you see a spike here in the purple, a larger spike here, and a little bit less bright, less extreme purple, a spike here in the blue, and a spike here in the red. These four spikes are the characteristic signatures of hydrogen gas and hydrogen emission. And different elements produce different fingerprints that make them uniquely identifiable. And all you have to do is take these elements, put them into a gas form, send electricity through them, and measure what the pattern is for each of these elements. Or you can even calculate them from the Schrodinger equation in simple cases. If you just do this, you can figure out what the pattern is of any element, and therefore you can identify from light emitted by some other object what it's made of based on what patterns it has in its light. And that's exactly what we're going to do for the sun. The other thing that I want you to recall back from the last lecture is that even though you can get these sharp lines from diffuse gases that have electricity going through them, when denser materials emit light, the lines get smeared out into what we call these black body curves, where you have this relatively smooth, skewed bell-like shape of light. So here again on the y-axis, I'm showing the brightness of how much light is being emitted. And on the x-axis, I'm showing the color of light, or in this case, the wavelength. So let's take a look at what the spectrum of the sun looks like. So here I'm plotting how much light you get from the sun, how much sunlight there is at every different color of light. And the first thing that you'll notice is that the sun spectrum looks very much like these black body curves that I've been showing. And that's because the sun is very dense. There's a lot of material there and it's packed into a very small area. If you compare the sun spectrum to these black body curves that I've been showing, what you can find is that the sun has light that peaks in the visible range. So the most light that the sun puts out is around 5,000 angstroms, or 500 nanometers. This is the wavelength of green light, basically. If you compare this to curves of other objects and objects of different temperatures, what you'll find is that if you compare this to the curve of a 3000 Kelvin object, where Kelvin is a unit of temperature that physicists use that's very similar to centigrade, it's the cooler object, the 3000 Kelvin object, peaks in the red. So we know the sun must be hotter than 3000 Kelvin. Same thing with 4000 Kelvin. The peak is right over here around 800 nanometers. For 5000 Kelvin, the peak is over here around 600 nanometers. The closest one we get is the 6000 Kelvin peak. Now, it turns out that if you do this calculation in detail, you find that the sun's temperature is pretty close to 6000 Kelvin. It's about 5700 Kelvin. This is about 5400 degrees centigrade, or about 9800 degrees Fahrenheit. So the sun is very, very hot is the first thing we can know. And that makes sense. We can feel the sun's heat on our face in the summertime. The sun is so hot at 5700 Kelvin that it must be made out of gas. There are several different phases of matter. We're familiar with solids like ice, we're familiar with liquids like water, and we're familiar with gases like steam. The hotter you get, the more likely you are to be a gas. And exactly that's what happens with the sun. There are no materials that can remain liquid or solid at such a high temperature. So the sun must be made up out of gas. So, what kind of gas is the sun made up of? What are the elements that make it up? To look and to investigate this, what we can do is we can look at these little lines here, these little dips in the brightness of the sun at different colors. These are the fingerprints of the elements, like I was talking about earlier. If you take a careful look at the sun, here's a way of looking at the spectrum of the sun, the amount of light from the sun at different colors. You can see these little black bands. These bands are, again, the fingerprints of the elements that make up the sun. Here's a big one here. Here's a little one. Here's a couple of big ones that come right next to each other. And all of these little dark lines are places where there's less light coming from the sun, and therefore there must be something in the gas causing those lines to exist. And we can go through and we can identify what elements are causing each of these lines. Here's just a very small section of the spectrum of the sun. And you can see here that you have a line from nickel, iron, calcium, iron, manganese, iron, titanium, hydrogen, silicon, iron, titanium, iron, etc. Tons and tons and tons of these lines that help us know that all of these elements must be present in the sun. So I just listed off a bunch of different elements, but how do we know which ones are the most important? Is it the ones that have the most lines? If that's the case, it looks like there's a lot of iron lines here. Maybe the sun is mostly made up out of iron. Is it the ones that have the biggest lines? In this case, you can see that the biggest line here is the hydrogen line. It's got this much larger and deeper profile than the others. So how do we do this? How do we go from these spectra, which show all of the different lines of all of the different elements, to figuring out how much of each element there is relative to the other? The first person to do this reliably and correctly was Cecilia Payne, who later married and became known as Cecilia Payne-Gaposchkin. And what she found is that hydrogen and helium are over 1 million times more abundant than many of the other elements in the sun. Overwhelmingly, the sun is made up of hydrogen and helium and basically nothing else. Everything else is just a little bit of stuff mixed in. So most of the spectral lines that you can see here are due to this trace amounts of stuff, and this big hydrogen line really betrays most of what's in the sun and most of what makes up its mass. So she ended up getting these results in the 1920s. This ended up being basically correct. In most recent numbers, there are some adjustments here or there, but for the most part, Cecilia Payne was totally correct, and hydrogen and helium make up almost all of the mass of the sun. Interestingly, this was against the prevailing wisdom in 1925 when Payne first published this. When this first came out, the prevailing notion was that stars were made up of a very similar mixture of elements as the Earth, which is different from what Payne found. When we look at the Earth, we don't see much hydrogen and helium. We see lots of rock, lots of iron, lots of silicate, lots of magnesium, stuff like that. So because this was such a revolutionary idea, Payne's advisors, she was a graduate student at the time, advised her to not necessarily claim that this was actually what happened. So in her thesis, she wrote down that although she believed that her calculations were correct, there must have been something else that caused these hydrogen and helium to appear to be so much more abundant than what everyone knew to be the case. So she backtracked a little bit from her conclusion. Within about 4 years, though, it became pretty well understood among astronomers that Cecilia Payne had been right all along, and that she was the first to really understand that the stars, and basically the entire universe, is mostly made up of hydrogen and helium.